Hi everyone, welcome back to another devlog on OGLRenderer. This might be the last update for a while, however, that's for a good reason. With this update, I finally achieved the original goal I set for myself when I first started learning C++, OpenGL, and computer graphics a few years ago, and that was to build a real-time 3D rendering engine from scratch that can deliver photorealistic results using state-of-the-art techniques. So what's new with this update? This update brings full support for PBR, physically based rendering, along with IBL, image-based lighting. I'm demonstrating it here using a GLTF 2.0 model, popular damaged sci-fi helmet. Let me walk you through how it works visually. First, with both the directional light and IBL turned off, we fall back to a minimal ambient turn, just enough to keep the model visible, but it clearly doesn't feel grounded in the scene. It feels disconnected. Now when I enable directional lighting, the model starts to look much more physically accurate. You can see how its roughness, metalness, and base color all interact with the light source in a physically plausible way. But something's still missing. It doesn't feel like part of a real environment. And that's where IBL comes in. Once we enable IBL, the leap in realism is huge. The helmet now reflects and reacts to its surroundings. It picks up the specular highlights and diffuse lighting from the environment map. Suddenly, it feels like it belongs in the scene. To show this even more clearly, I can swap the lighting environment from a snowy field to an indoor bar scene with warm lighting. Notice how the entire appearance of the helmet shifts, from the cold whites and greys of a snowfield to a much warmer yellow-orange hue. This dynamic responsiveness to the environment is what makes PBR and IBL so powerful. What makes this scene even more visually appealing is that this model makes use of all the standard material maps: albedo, normal, ambient occlusion, roughness, metalness, and emissive, just like you'd find in a modern game asset. And you can see, if we disable all of the lighting, some parts of the model are self-lit by the emissive textures. To validate the realism of my render, I compared the outputs side by side with Khronos Group's GLTF viewer and Blender's path-traced rendering engine cycles. As you can see here, the results are almost indistinguishable, which means the renderer reflects the ground truth well, even when compared to offline rendering. At this point, the only paths left for further graphical fidelity would involve cutting-edge techniques like NVIDIA's Restir for real-time path tracing, or some kind of dynamic global illumination system, based on something like RTX-GI. However, those are still being actively researched and go well beyond the scope of a hobby project like this. Now, I did have a longer roadmap planned, but given where the renderer is now, I'm choosing to sunset this project for the time being. I'm going to shift my focus towards learning Unreal Engine, so I can apply everything I've learned about C++, rendering pipelines, and graphics to a larger scale, industry standard product. That said, if I find myself working close to engine code professionally, especially at the graphics API level, I might revisit this renderer, maybe even complete that Vulkan rewrite I was planning on. Thanks so much for watching this series, and for following along on this journey. If you're interested in where I take things next, especially as I dive into Unreal, feel free to subscribe. Until next time, cheers.